Good morning, all. I'm sure now you are very fresh and energetic after your vacations, and you have enjoyed your vacations as well as done some programming also. I'm sure all of you have tried with the practice problems which I had sent to your CR, and most of those problems had various questions of difficult level and easy level as well, starting from your control statements and your arrays, strings, etc., etc., and data structures also. So those who are weak in the programming, they can start slowly by these programs and then subsequently try to do with the data structures effectively up to stacks I have done. So polynomial, sparse, etc., all those have been done. And you must practice all of these or most of these. And I have also given one assignment sheet to CSA sections, and they are already knowing the deadline. So assignment problems are less than the practice problems. So you have to submit the handwritten solution of these. Well, proceeding further, let's resume where we have left our previous discussions. So till now we have discussed the stacks, and the stacks you have already used with a property of LIFO. So you know what is a stack and how does it work well now. You have used a stack for solving problems like infix to postfix conversion or postfix evaluation, etc. But it is obvious that stack might not be suitable in all situations. For example, if you go to a bank or if you are in a shopping mall, so you have everywhere the list, the number of people waiting in the line, and obviously LIFO property won't help at that stage at all. So you normally stand that in a line and you call that as a queue. And effectively, queue is another data structure which is formally used in computer engineering and IT, etc., for doing special programming similar to stack. The data structure queue has a special property. So it's a data structure with FIFO property, where FIFO stands for first in, first out. So the one which has been put into the queue for the first will be the first to be serviced. And this is what exactly we experience in our bank queue or our bus queue or train queue or shopping queue or anywhere where we are. Then normally we prefer first come, first serve. So that is the service which we normally achieve. So stack was a LIFO, but queue is an FIFO property. So whenever we say queue as a data structure, corresponding to data structure as an ADT, so we always look at its storage and we also look at its operations. So let's understand both one by one, and we will understand. It's very similar to queue. So understanding queue, it's very similar to stack. So understanding queue will be such an easy job that it will be just simple and similar to what we have now. Storage. Of course, for the time being, we are going to store it as an array, but later we are going to do it using linked list also. So initially array will be a good enough data structure. Let me just see if focus can improve. I think that's good enough. So you have the corresponding array as a data structure, which we are going to use for the storage. And correspondingly, you need certain indexes. In case of a stack, like you used top, here we use two different indexes. One we call as a rear, another we call as a front. Like when you are standing in a queue, obviously a rear end means the last end, the back end on which people will keep on joining, and the front end will be the end on which the service will be provided. So front end is used for the deletion operation, delete from this end, and rear end is used for insertion. For example, if let's say I'm standing in a bank for the cashier. So let's say if I have my bank cashier here. So I normally will say that the queue is growing like this. These are the people standing. So this I will say as a rear end so that more people can join. And service provided will be towards this end, and this end I call as a front end. So this is front of the queue from where the service will be provided, and people will keep on joining to the rear end. So this is what we call as the storage. Then comes operations. So just like in case of a stack, we had operations like push and pop. In case of a queue, the operations are insert into queue, or called as, say, insert queue, and then delete queue. So delete from a queue, maybe you could say delete queue, whatever name you want to give. So these two operations are obviously for insertion and deletion. Remember, these should not be called as push and pop, which will be incorrect name. And for queue, push and pop are never words used. They are explicitly used for stack only. So here you will say insertion into a queue or delete from queue. Then, of course, like in stack, we said here also we can have is queue empty and is queue full as a Boolean operations. And like in stack, we said that they will help in maintaining the modularity, etc. So they can be the Boolean functions returning true or false. So if the stack is empty, is queue empty will return a true and otherwise return false. And similarly for the is queue full also. Where internally at the system level, true effectively is used as 1 and false is always used as 0. Having said that, let's start understanding. So let's say I have this as array. So I'm going to store it as an array. Now, obviously, array means it will have a 0 to, let's say, max. So max minus 1 will be the last index. So I can define max as 150, whatever you require. And for verifying the fullness, etc., you can reduce max and confirm and do all that. So obviously, for the time being, I will have int, let's say, q as an array. So I will say, let it be named as QUEUE for the time being. And I declare it as of max size. And max, as we have already done using hash defined, etc., we can do that. Then we will have two ends. One end we call as a front. Other end we call as a rear. And we have to give them initial values. For the time being, we are using them global as we have been doing earlier. Later, we will be doing it through parameters. So only for the time being, we are taking them global. What should be the front and rear initial value? So like in top, we said top always points to the topmost element of this. So here also the same thing will happen. Rear will point to the last filled location, and for maintaining the uniformity, they are also initially declared with or initialized with -1. So -1, the logical reason of using -1 is presently list Q doesn't exist. Q has no element adding at all. So Q has front and rear outside of the Q, and at present Q has nothing in this. Once Q gets activated, Q will have certain elements. So valid indexes from 0 to max -1 will get used. In fact, once I defined this, everything is well defined. So I have here initially your front end also here, and I have your rear end also there. Slowly, what will happen? So I will say, I will be inserting some data. Let's say I have inserted 4, 9, 6, 7. So through this process, effectively, everything is defined that when I have used rear as -1, for storing element, initially rear will be incremented and I will be storing. That effectively will mean that my rear will reach to this end, which has been initially till now entered or data has been stored. So up to this, it is full and remaining are empty available. Similarly, for the time being, front is pointing as -1. And at present, the first element to be deleted can be 4. And whenever I want to delete 4, the correspondingly deletion will happen, and later you can further continue deletion. So my insertion and deletion both will be possible using front and rear end. Obviously, 4 was the first to be inserted, so 4 should be the first to be deleted. Similarly, after that 9 was inserted, 6 was inserted, 7 inserted, and after insertion of 7, rear is here. A new element will come, let's say 11 is inserted, so insertion will happen here and rear will shift. And further insertion. Similarly, deletion will happen, so front will shift, this element will be deleted, effectively mean this will become empty, and now front will reach to this location. And process will continue like this. So this is how my queue works. So at some point of time, I can easily see, say 4 deleted. Later I say, let's say front was also further upgraded and 9 was also deleted. So at some point of time, now I will have front pointing here. It means 4 and 9 have been deleted already. And insertion happened with order 4, 9, 6, 7, 11. These have been inserted. So if these have been inserted, my data will be something like this. And this was index 0, 1, 2, 3, and maybe this is 4. At present, my rear is on this point. And further it can grow. So some presence values are empty here also available, and we are getting my front and rear shifting accordingly. Now, based on that, we are supposed to implement our operations. I say, after explaining everything and after telling you the initial values, probably you can easily implement insert and delete without any difficulty. So I'll give you time for 2-3 minutes to think of doing insertion and deletion automatically without me explaining anything. Why? Because it's damn easy now, and the logic is exactly parallel to where we have worked with the stack, and initial values describe how they will be processed and implemented in which execution sequence. The only thing which I need to understand is whether insert queue function will be returning something or not. So I say normally its purpose is to store the data until unless it was having a full problem. Otherwise, we will be storing, and default it will mean nothing to be returned. The value which we are going to store, because it's a function, as in stack we did, so the value which is to be inserted must be passed as a parameter, and I should be able to store this value into this insert queue. Similarly, if I want to write a delete queue, deletion from the queue will mean no parameters to be supplied because nothing else outside is to be told for deletion, and deleted element is to be returned. So I will say, in this case, that the return type is int. So I will be writing int delete queue. So try this code. It's quite easy. I'm giving you 2 minutes, 3 minutes to try this. And after that, I will resume with writing the code for those who could not write themselves. So I'm pausing here. Those who want to try, they can pause the video and try that. Otherwise, you can see the video once you have done. So if you have tried already, now you can resume. So after pause, you can resume and now verify whether you have done correctly or not. So let's go insertion. Void insert queue. Once you are saying insert queue, parameter being supplied, all other variables like queue and front rear being global, things are easy. Insertion always happens at a rear end, so we are supposed to update rear. Of course, if queue is not full, only then insertion will be done. So I must check, is queue full or not? So I will say if queue not full, some condition for that must be put. That we will see what should be the condition. If queue not full, only then we will have. So I will say if queue full, I will give a message printf insertion not allowed as queue is full. And we will say it is not allowed for the time being. Else we are supposed to do the insertion. How to do that? Using rear end. Remember, initially rear points to -1. -1 is invalid, so that straight away tells that first rear is to be incremented and there is guaranteed space available. So rear will be incremented and then I should be able to store the data into the array. Array name is QUEUE. Rear is the address or index on which it will be stored and the value to be inserted was val. And that's it, done. The only thing is how to check full. So when the queue will become full, just a recall, if you have this queue, you have rear and on, let's say index 4, and you had 11 stored here. So you have plenty of space available. Ultimately, you have the last index as max minus 1. So if you have max minus 1, then you are going to store the element up to this index. So just see, the condition has to be something related to rear versus max minus 1. Now what? If rear is, let's say, just before max minus 1, is it full or not? Like rear reaches here. Is it full? No, because this location is full, this is empty. So when this gets full, rear will reach here and then it will be full. So effectively it means if rear becomes equal to max minus 1, then the queue has become full. Whether you write equal to or you write greater than equal to also, so that will be fine. So ideally I will say this condition will mean if rear equal to max minus 1, effectively the queue has become full, else I can easily do the insertion. Let's look from the deletion angle now. Int delete queue and no parameters. What we have to do? If the queue is empty, deletion not allowed. So first condition must be if empty or not. If the queue is empty, then we are not going to permit the deletion. So we will check that. The condition we will decide. But if it is empty, we will avoid printf message because status is to be returned. So maybe I will say the way we did earlier, I will say, let's say return minus 1000, assuming that the empty situation is being returned. Empty represented via minus 1000. So this will be returned. Else deletion is permitted. How to do? Using front variable, using front index. Front is initially minus 1. So guaranteedly first I have to increment front. And because queue is not empty, that means there is guaranteedly some data available at the next to front position. So that is to be deleted. Front plus plus, because initially front was minus 1. First element stored was at index 0. So front plus plus. And then effectively the element is to be returned. So this becomes return equivalently for queue. It is equivalent to saying that help is deleted, but of course it will be overwritten and then only the previous value will vanish. But for our purposes, it will never be reused because front will always point to the next position in the next deletion. So this way I am able to delete without difficulty. For example, if we said that in the previous example, we have said that my front is pointing to this position, effectively meaning that this has been already deleted. The next to that was 6, then we had 7, then we had 11. Here is your rear end. So the next element to be deleted is obviously 6. So first of all, according to this front, this will shift to next. This value will be extracted and returned, and then this is equivalent to being empty. Later, let's say again a deletion. So deletion meant effectively 6 being returned. Again a deletion call comes. So deletion will again mean front to be shifted. Shifted means now reaching to this element, 7 being returned, and effectively front will point to this end, rear to this end. Then again a deletion, let's say called, So deletion will mean front again shifted, 11 deleted, and now my front is also pointing to this end. So I can easily see if a front and rear reach to the same place, the queue has become empty now. So probably I can think something like this to be the empty condition. Now, probably I'm saying because I have to verify that in all situations this is correct or not. We have just seen that after certain deletions, once 11 got deleted, front is pointing here because front deletes from the next position. Rear was this position where last entry happened. So now queue has become empty. Initially also you can verify. Initially what was there? Front also -1. Rear also -1. So at that point also queue was empty. Both were -1 and still that time this condition will be perfect. So for all those situations, this can accordingly be coded without difficulty. And accordingly, you can write your is full, is queue full to return a true or false. So you should be able to write the suitable condition to return true or false. And similarly, for the other situation, also for the queue empty. So those functions also you should write, and they will be used to verify, to check their status whenever needed. Now, having said that, I can see that the basic working of the queue has become good enough, but compared to stack, we have here certain more issues coming up. For example, let's say max was 10. If 10, that means I have a queue to store total 10 values, 0 to 9. Now, let's say I did 10 insertions and inserted value 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So my rear has reached here. Perfect, no issues. Let's say after 10 insertion, I have deleted 5 times. Effectively means first time 1 got deleted, then 2 got deleted, then 3 got deleted, 4 got deleted, 5 got deleted. All these are deleted. So my front has reached here. And all these locations are effectively free. But now just if you call insertion, it will tell queue is full because my rear has reached to max -1. Although I can see there is a space available before front or up to that, but that will not get utilized because my condition of fullness is always with respect to rear. So I need a solution to this. Of course, now you can think of a solution that like I need some kind of data shifting. But shifting of data every time with insertion is not to be done because my insertion or deletion operations are always said to be unit time operations. Unit time means they should not use any loop and they should get executed with fixed number of statements 1, 2, 3, 4, 5, 7, 10, but no looping, etc. to be done. Because loop means or some n times step to be repeated, and if n is very big, it means a lot of time. So max could be 99,000 or whatever, and unit time means fixed line of statements should be done. So loop is never normally permitted when we have basic operations of a queue. Hence, I can't say that every insertion should do this shifting. So every insertion shifting is not the solution. Because that will mean every time some number of elements, whatever number of elements are there from front to a rear approximately, all them to be shifted will mean a loop to be done. So shifting is not a solution for that. Although we can see space is already there. So in such situations, normally what will be done will be that a compact operation will be implemented, and not every time it will be called, but sometimes as per necessity, I will say compact queue operation can be implemented. Where compact queue will mean that if inside the queue there are some initial spaces available, your data is stored, let's say from index 70 onwards up to 99 if max was 100. So this is a full, and front has reached to, let's say, 69. Then effectively 0 to 69 is empty. These places are empty. Then I would like to have this queue readjusted in a way that element from 70 to 99 get shifted, and they are stored from 0 to 29 as full, and all free space is available here onwards. So earlier this was a free space but could not be utilized. Now this free space is shifted towards right, and that will automatically mean that we have to shift back all elements present. So I can do all shifting by copying back all values, like this value, 70th value to be copied at index 0, 71st value to be at index 1, and so on. Not only that, secondly, the rear end index and front also to be updated accordingly, because now they will change their actual position. Like that will mean my rear should be now 29, not 49, 99, and maybe front to be -1 again, so that the deletion and insertion in future become without difficulty. So I should be able to do this. Hence, you can easily write your loop and code to do compaction. And we say that compaction operation can be specifically called whenever needed, or maybe I can make certain thumb rules. Whenever queue has become 80% full, maybe compact queue can be internally executed, or I can explicitly call whenever it is fully full. Whenever fullness has come, I will check whether it is possible to compact, then do compaction. But the advantage being, this is not done every time, not done with every insertion. Hence, my insert and delete operation normally remain unit time, and very few times the insertion will require compaction to be done, and compaction will obviously take time, and it will require certain execution steps in terms of n, etc. So this will be done, and now based on that, I will say this could be one solution, and compact queue could be there. So I will say note down your homework. Now what you have to implement queue and its operations, and the way we did in case of a stack, implementation should take care of providing repeated choices in the main to repeat till we select exit, and the choices for various operations like insertion into the queue, delete from queue, Then similarly, I could say display Q contents to verify whether my Q is correct at all times or not. Fourth operation I can give for compaction. And 5 I can give for exit. So till I don't select exit, process to be repeated. This we have done in for case of a stack also and here also. In case of a compaction, you have to remember one thing, that while copying back, you should not overwrite certain positions. Whenever you are doing such kind of a shifting in any logic development in array or in any other subject also, you have to be always careful. Like it was possible that you shift this element to appropriate address first, then shift this element and so and so. Or you start from this element shifting and copying to that. Both from both ends could be done, but one of them could be erroneous, could be faulty. For example, let's say 70 onwards data is full. 70 to 99 data is to be copied from 0 to 29, obviously. So one way could be that you will copy element 70 to be at a 0th position, and so 99 will come. So you first copy 70 back to 0. That will mean effectively your I minus 70 will be used, and your I can go from 70 to 99. Perfect. Other way. Second alternate could be that you have still the same thing to be done, but you say you will do I minus 70 copying, where I starts from 99 and goes up to 70. Still, it will do the same thing, that from I, the element copied to I minus 70, no problem. But just imagine if the data was filled from 40 to 99. It is full. Now, that means minus 40 is to be done. So if you say 99th element to be shifted or copied to address 99 minus 40, because elements of 40 to 99 will ultimately go to 0 to 59. There are total 60 elements. These are total 60 elements available. So they will be at 0 to 59 now. And that process will mean 99th shifted to this. Similarly, 40th shifted to 0. 40 minus 0. 40 minus 40. So minus 40 fixed remaining. And this I changes. But now becomes a problem. 99 minus 40 actually means 59. 59th location has some data here. If you copy 99th and by that time 59th data has not been shifted back, you overwrite 59th location. So from in this case, this will become problematic, and you should take care or be careful that from which end the shifting to be taken place. So from which end you should start shifting, that should be chosen carefully, that you don't overwrite the shifting process. So you have to, you should not overwrite some data which was already present. So be careful from which end shifting should start. Choose carefully. Having said that, I think skews discussion is more or less over. Just I will wind up with some additional discussion, that is compaction the only solution? Because compaction still needs Q, still needs a loop, and is this the only solution? And if it is only solution, of course, it is time consuming. Can I have solution without looping at all? Without compaction or something, and still unit time operation without loop or compaction? Yes, you can do that. And the answer to that is that why should I do compaction? I say, while shift copying, let's say your front has come somewhere here, you reached to this end as rear. Then, although you say that you can't go beyond, but because these locations are free, you can bring your rear back to this place, bring rear back to 0 if you reach to the last boundary, provided there was space. So if Q is not full, you can shift your rear back to this. Similarly, later, front also can move back to this position. So I say such kind of a concept is called as a circular Q, and it will not require compaction to be done. What it says? It will simply say, like doing in insert Q, whatever function you were writing, if Q is not full. So how to check that? We will do. So if Q full, obviously we will give the message. I'll say if Q full, whatever logic was there, message, etc. Else, if Q is not full means guaranteedly I am permitted and there is some space available. What to do? Earlier I was doing the rear plus plus. Now rear plus plus might not be sufficient because at this point rear plus plus will not work. So for all other positions, rear plus plus is okay. But if rear reaches to the last end, then we have to do different. If rear reaches to max minus 1, then what I have to do? So I'll say else if rear is equal to max minus 1, rear should become 0. Else rear plus plus is okay. So for all other boundaries except when rear reached here, simply rear plus plus. If it was 50, let it become 59. If it was 90, 91, 98, 99. But if it is 99, then let it become 0. And next time, now it is 0, again plus 1, again plus 1, again plus 1. So every time rear plus plus is okay, except for the boundary this. And that's it. Once you have done this, then the rest of the logic is same, that you will say Q rear equal to val. So whatever you were doing, same logic. So just instead of rear plus plus statement, I need logic like this. The rest is same. And similarly for the front also. When front reaches to 99 or max minus 1, the similar logic to be put there also, that front becomes 0. First time initially they are outside, they are minus 1, but subsequently they will keep on revolving between 0 to 99. So it's a circular Q. You can see it's like circularly rotating among these once you start. And they will revolve around 0 to 99 always. Rear will also revolve around 0 to 99. Initially, they could be outside, not a problem, but once come, everything will still work. So, of course, I have to take care of fullness and emptiness also. We have to verify that we know they are full or not, they are not full or not empty. This will work. Then I say, there is a similar now additional smart way of writing the same statement. This all statement can be simply written by writing rear equal to rear plus 1 percentage max, where percentage means it's a mode operator. Remainder. So this situation can be solved by using remainder operation and no if to be written. Rear, let's say if it is a 10, then it will become 10 plus 1, 11 percentage. Let's say max is 100. Remainder will be still 11. Okay. When rear was 99, so if rear was 99, it will be 99 plus 1 percentage 100. It means 100 remainder 100 division will effectively mean 0, and that's what we wanted. So for all other values except rear being 99, the remainder will be the incremented value directly. And that will be directly stored. For all other, even if it was 0, 0 plus 1, 1, percentage 100, still 1, 10 plus 1, 20 plus 1, 90 plus 1, 95 plus 1, all okay. 99 plus 1, this remainder becoming 0. So this whole statement can be simply written like this, and similarly for the front also. But I'll stop here and say probably my full and empty condition will get disturbed. Earlier, I was able to simply say empty with front equal to rear, fine. But now how to check fullness? And probably that is going to be more problematic. Front equal, rear equal to max minus 1 is no longer true. Obviously, that will mean front versus rear, the decision has to be made. But can I design a correct condition which will be able to differentiate between full and empty? We will see in the next class, in the coming class. So I will leave it to you as an extra practice problem, that implement Q as a circular Q, optional work, implement circular Q the way we have done other Q, and think of condition for fullness. Can you find certain condition? If yes, that will be an excellent logic and you will be doing an excellent work. If not, maybe next class I'll explain and we will resume from there. So I'm sure all of you will try, and tomorrow we will discuss further. Bye-bye, all the best. So homework you have to do, and extra practice problem for circular Q. Homework is related to Q, and practice problem for circular Q and its fullness. Bye-bye, all the best.